Okay, so for this week's session, we're going to discuss different forecasting models. And this is actually one of my favorite sections for operations management and forecasting because it really opens up an entire world of being able to identify needs and resources, identify when those needs and resources will change. And really, it's kind of like holding a crystal ball in our hands. So this is one of the most valuable tools that we can use in operations management. And there's a number of different methods that we use because there are a number of different items that we may need to forecast or demand situations. For example, sales demands can fluctuate seasonally. They can fluctuate steadily on an incline or decline as a product goes through its life cycle. Or there may be other types of demand fluctuations. So depending on how the sales demand fluctuates depends on which model will be the most accurate. Similarly, there may be other things that we want to forecast that may or may not affect demand. So, for example, we may want to forecast population or fuel price changes if we're looking at forecasting cost changes for production. It may be the cost of metal fluctuations. It may be the availability of human resources. So we may look at population of a particular area before we look at putting a particular plant somewhere. So there are lots of different things that we may need to forecast for. And what we'll be able to do today is look at a couple of different models that allow us to forecast different methods and how we tell which one is the most accurate and how we forecast for the next period or the next step. So the first one we're going to look at is a linear regression model. And so what I've done is put in the data for hits and orders. So the baseball field wants to see if the number of hits affects how many orders will be placed in the concession stand. So they believe that there's a trend or a connection between hits and orders. Now there's a difference between, and this should be noted, there's a difference between correlation and causation. Just because there may be a pattern between two does not mean that one necessarily causes the other. Linear regression helps us identify whether or not there is causation. In other words, does the number of hits directly cause the number of orders, or is there a correlation in that does the number of hits does the number of orders seem to go up at the same time as the number of hits? Now, obviously, a hit can't cause somebody to order food. So in this case, we're looking at correlation over causation. So we have our number of orders and our number of hits here, and we're going to do what's called a linear regression model. And in Excel, we can do data. And, sorry, my screen, there we go. We're going to do data and data analysis. If you don't have the data analysis tab, you'll need to go into File and Options and add that tab. And add the tool. So let's go through that process real quick just to make sure that everybody has the data analysis tab. So we go to Options, Add-ins, and here it says Excel Add-ins, so we say Go. And you want to make sure that you have this analysis tool pack checked. And then from there, once you have that, you should get this data analysis. If not, you'll want to right-click here, and you can customize your your ribbon so that you have the data analysis option. But it should appear automatically once you add that tool pack. So once we have data analysis, you can see there's a number of different options that we can do. In this case, we're going to do a regression. So we say OK. And I like to think of the Y as being, why is this happening? So it helps me identify which one should be Y and which one should be X. So in this case, we're looking at orders. We want to know why orders change. Do hits correlate or cause the number of orders depending on which we're looking at? So Y is our orders, so I select the Y. For X, I select our hits. And I highlight the labels and click this labels box. That just makes the data come out a little bit cleaner. And you'll see in just a moment. And I'm going to have this go to a new worksheet. So now our data's in here. So we look at a couple of different points on a regression analysis. One is this statistically relevant? In other words, is our data clean and neat, and is there some sort of relationship between the two sets of data points? And for that, we want a significance F of 0.05 or lower. In other words, it's got a statistically significant, it's statistically significant at 95%. And so we are definitely below that 0.05. So definitely have a good significance here. Our R squared and multiple R, this also gives us a good indication. So our R squared is one way of saying that in essence, 55% of the orders can be explained by the hits. So the data relates about 55% of the time. So not a really great relationship, but a decent one. Our intercept and hits. Now this goes back to our first algebra class where we learned y equals mx plus b. So this is for the slope of a line. So if we were to graph these data points, we would see the slope of our line at y equals mx plus b. And b being our intercept and m being our x coefficient. So in this case, our formula is y equals 0.151 times hits, I'll put a parenthesis around that, plus our intercept of 1.317. So now we have a formula to forecast or predict the number of orders based on the number of hits. So we're going to carry that over to our original data set. And here I'd already had it plugged in, but now we have this piece here. So we can take a look now, and you can see I have the formula. The forecast for 34.2 hits would equal 0.151 times the number of hits plus 1.137. So based off of 34.2 hits, using our formula, we would estimate that 6.48 orders would be placed. So when we carry that down and we use that formula all the way down, we can now estimate how many orders for each of these existing or known data sets. So we can look at how different our forecast would have been from our actual data to help us determine how accurate this model is going to be. And we can also look at the very next set of data. So for example, if we wanted to forecast at 60 hits, we would carry that formula down, and at 60 hits, our forecast would be 10.37. But we need to know that range of error. In other words, that give or take. So to calculate error, we want the difference between orders and our actual orders and our forecasted orders. And the reason I have ABS here is we want the actual difference. We don't care if it's plus or negative. We just want to know the difference to the right or left of the number line. So we use the absolute value formula, or ABS, to get the absolute error. And again, we carry that down here. So our average absolute error, or our mean absolute error, is 1.02. So we say that our forecast for 60 hits would be 10.37, give or take 1.02. And if this was in thousands, we would ultimately round this to 10.4 or 10,400. So this error and mean absolute error then allows us to cross-compare different models. So the next model that I want to look at is actually using a different data set. And for this, we have 8 months of existing data, and we have the demand for a particular product. And the first one we're going to use is a 3-month moving average, or MMA, 3MMA. And for a 3-month moving average, for the first 3 months, we can't calculate anything because we need 3 months of existing data to be able to forecast the demand for the next month. So we're going to use average, and we're going to average the 3 prior months. This tends to be more accurate with seasonally fluctuating demand. So if every 3 months the demand changes, or every 6 months the demand changes, we can use the prior 3 months as a guessing point for the next set of data. So then we carry this down, and you'll notice that our formula now moves for month 5, we're going to use 2, 3, and 4. And for month 6, we're going to use 3, 4, and 5. So it's a moving average. And now we want to get our error. And again, we can't do anything with the first 3 months. So the next ones, we're going to use our absolute formula and calculate the difference between the actual demand and our forecasted demand. And we're also going to forecast for month 9 based off of our 3-month moving average. So we just carry this down, and you'll see it's using the 3 months prior, 6, 7, and 8. We don't have an error for 9 because we don't have actual demand data. This is our actual forecast. So down here, we're going to do our mean absolute error. And I'm going to change these all to 2 decimal points so we can see a little bit better. And so our mean absolute error is going to be the average of just our errors. And the reason we use average is so that it's only calculating those that have data in those cells that have data in them. Otherwise, if we tend to be off in counting the number of items by manually calculating average, we can throw off our decision as to which one is the most accurate. So for this one, we would say our forecast is 10.33 for month 9, give or take 2.07. So that's almost a 25% give or take. Not great, but let's see what other options we have. So the next one we want to look at is a 3-month weighted moving average, or 3 WMA. And for that, we need to weight the prior 3 months. So it's very similar to our 3-month moving average, but now we're going to weight these 3 months according to when we feel the data most closely resembles the next month. So if we feel that the data changes month to month, then the closest month is going to be more closely resemble our current month that we're trying to forecast. So in this case, we have weights of closest is 0.55, middle is 0.33, and furthest is 0.12. So again, we can't do our first 3 months, so we're going to say that, and this is a very important formula because anytime we do probabilities or weighted outcomes, we use this exact same formula. So this is anytime we do a weighted problem or a probability outcome problem, we're going to be multiplying the probability or the weight times the outcome. So we're going to take our most recent one. So month 4 is closest, or month 3 is closest to month 4, times the weight for closest. And I'm going to use my F4 key to lock down. I've got the dollar signs on both sides. That's going to lock down this closest cell so that it doesn't change. And the reason that I use this instead of typing 0.55 is if I needed to change my weights so I didn't have to change it in every single line item, I can change it up here, and as long as it's referencing this cell, it will change the rest of the formula. And we're going to add the middle one times our middle weight, and again hit F4, and you'll notice that I'm not using F4 to lock down our demand cells because those ones we want to move down as we move the formula down. These ones we want to stay in the exact same position. And then I'm going to add in my furthest month times my furthest weight, and again F4. And it may be function F4 if you're using a different laptop, different type of laptop. And we hit enter. And again, we're going to carry this down to month 9 so that we can see what our forecast would be for month 9. So you can see already there's a slight difference. With the 3-month moving average, we forecasted 10.33. But with the 3-month weighted moving average, we forecast 10.77. So now we want to calculate our absolute error again. So our demand minus our forecasted amount. We're going to carry that down, not to include 9 because we don't have actual data for 9. And now we want the average error. So in this case, now we can look at these two models and we say that the 3-month moving average has the lowest average error, or lowest absolute error, because it's 2.07, so that lowest give or take. So now we can say that of the two models, we would choose to forecast using a 3-month moving average model. And then, of course, we could use a regression model, as we did in our first problem, to do a third comparison and determine if a regression model is even more accurate using the mean absolute error rate. Okay, I hope this helps. As we covered forecasting using 3-month moving average, 3-month weighted moving average, and a linear regression forecast model.